I'm Albert Einstein. I have been given a voice by artificial intelligence so that the science I spent my life uncovering can reach you today. Most people think of cold as an enemy. They avoid it. They layer up against it. They turn the shower to hot the moment the temperature drops outside. This instinct is understandable, but it is wrong, and the evidence to support that claim is not speculative. It is documented in peer-reviewed biology, thermodynamics, and cellular research conducted over decades. What the cold does to your body is not random. It is precise. It is selective. And it is, in many ways, the most powerful biological reset available to you without any pharmaceutical intervention. I spent my life studying how energy moves through systems. The principles that govern stars also govern cells. And when I look at what cold does to the human body through the lens of thermodynamics, I see something remarkable. The cold does not attack you equally. It finds your weakest components. It eliminates them, and it forces your biology to rebuild at a higher standard. That is not a metaphor. That is a mechanistic, documented biological process. And I am going to explain every step of it. If you want to understand your own body at the level of physics and biology, not myths, not wellness trends, subscribe now. Every video on this channel is built on documented science. That is the only language I speak. Let us begin with the fundamental principle. When you expose your body to cold, you create a thermodynamic challenge. Your core temperature is maintained at approximately 37 degrees Celsius. It must stay within a narrow range to sustain life. When the third-party environment drops significantly below that, your body faces a problem it must solve using energy. This is the first critical insight. Cold is not just a sensation. Cold is a demand placed on your biological energy management system. Your body responds to this demand by activating what researchers call the cold shock response. This is a cascade of molecular events triggered the moment cold receptors in your skin detect a significant temperature drop. The signal travels through the nervous system with extraordinary speed. Within seconds, norepinephrine, a catecholamine neurotransmitter and hormone, begins flooding your system. The increase is not subtle. Research has documented norepinephrine elevations of 200 to 300% following cold exposure. This single molecule is responsible for a remarkable range of downstream effects. Norepinephrine tightens blood vessels in the periphery. This is vasoconstriction, and it serves an immediate survival purpose. It redirects blood flow away from the surface and toward your vital organs. Your heart, brain, and lungs get priority. The cells at your extremities, the ones that are less critical in the short term, receive reduced blood flow and reduced oxygen. This creates a sorting event inside your body. Cells that are metabolically efficient, cells that can sustain themselves with reduced resources, survive this period of stress. Cells that are already damaged, poorly functioning, or metabolically wasteful cannot. They receive the biological signal that it is time to shut down. This process has a name. It is called apoptosis, and it is one of the most important, least understood processes in the human body. Apoptosis is programmed cell death. It is not random destruction. It is a highly ordered, genetically encoded process by which the body eliminates cells that are no longer useful or that have become a liability. Every cell in your body carries the machinery for its own death. This machinery is activated under specific conditions, and cold-induced metabolic stress is one of those conditions. Research in cryotherapy and cryobiology has documented this mechanism repeatedly. When cells that are already weakened through age, damage, chronic inflammation, or metabolic dysfunction are exposed to the thermodynamic stress of cold, they are more likely to trigger their own apoptotic pathways. They effectively collapse under a pressure that healthy, robust cells can sustain. This is what the thumbnail means. Cold does not kill cells randomly. It kills the weak ones. The strong ones survive. And then your body, sensing the reduction in cellular load and the survival signals flooding through it, begins rebuilding. The rebuilding phase is where the real power of cold exposure lives. When apoptosis clears out damaged or dysfunctional cells, your body's stem cell populations and regenerative systems activate to replace them. New cells are produced under the influence of the same hormonal surge that triggered the stress response. This is a cleaner, more functional cellular cohort than what was there before. The thermodynamic stress acted as a filter. What remains after the cold, and what grows in its wake, is biology operating at a higher baseline. I want to introduce a concept here that is central to understanding all of this. It is called hormesis. The principle of hormesis states that a small, controlled dose of a stressor produces a beneficial adaptive response, while a large, uncontrolled dose of the same stressor produces harm. This is not new science. It has been documented in toxicology, exercise physiology, radiation biology, and now cold exposure research. The dose makes the poison, and it also makes the medicine. When you exercise, you damage muscle fibers. The damage triggers repair. The repaired fibers are thicker and stronger than the ones that broke. You are not getting stronger despite the stress. You are getting stronger because of it. Cold operates by the same fundamental principle. A controlled, brief cold exposure creates a manageable thermodynamic stress. Your biology interprets this stress as a survival signal. Every system that can adapt, adapts. Every cell that can strengthen, strengthens. The weakest components are removed. The whole system upgrades. This is the logic of hormesis. And once you understand it, you see it everywhere in biology. What does not kill you, to quote the philosopher Nietzsche, does make you stronger, but only if the dose is calibrated correctly. This is why cold exposure protocols matter. Too brief and the signal is insufficient. Too long and you cross from hormetic benefit into genuine cold stress pathology. The right dose produces adaptation. The wrong dose produces frostbite. Now I want to take you deeper into one of the most fascinating mechanisms cold activates. It involves a type of fat tissue most people have never heard of. It is called brown adipose tissue, or BAT. Most people are familiar with white adipose tissue, regular body fat, which stores energy. Brown adipose tissue does the opposite. It burns energy to produce heat. It is metabolically active fat, and cold is one of the primary triggers that activates it. Brown adipose tissue gets its color from an extremely high density of mitochondria. Mitochondria contain iron-rich proteins, which produce the brown color. These mitochondria in bat cells express a protein called uncoupling protein 1, or UCP1. This protein does something remarkable. It uncouples the electron transport chain from ATP synthesis. Normally, mitochondria use the energy released from burning fuel to produce ATP, the cellular energy currency. UCP1 instead diverts that energy directly into heat production. The cell burns fuel and produces warmth rather than stored energy. This is thermogenesis at the cellular level. When cold receptors signal that the body needs to maintain core temperature, norepinephrine activates the BAT cells. They begin burning fuel at an accelerated rate. In adults who regularly expose themselves to cold, BAT volume increases. More brown fat means more thermogenic capacity. More thermogenic capacity means higher baseline metabolic rate, better blood glucose regulation, and improved lipid metabolism. Research published in the New England Journal of Medicine confirmed that adult humans retain active BAT deposits and that cold stimulation significantly increases BAT activity. This was considered a significant finding because for years it was assumed that only infants had active BAT. The implications are substantial. An individual with more active beat burns more energy at rest. Their metabolism operates at a higher baseline. Cold exposure, practiced consistently and within safe parameters, literally increases the metabolic machinery available to your body. This is not a passive benefit. It is an active biological upgrade triggered by thermodynamic stress. Let us now discuss a process that connects cold exposure to cellular longevity in a direct way. That process is autophagy. The word comes from the Greek for self-eating. And while that sounds alarming, it is one of the most beneficial things your cells can do. Autophagy is the cellular cleanup process. It is the mechanism by which cells identify damaged proteins, dysfunctional organelles, and cellular debris, and break them down for recycling. When autophagy is working well, cells stay clean and efficient. When it is impaired, as it is in chronic inflammation, aging, and metabolic disease, the debris accumulates. Cells become less functional. Diseases associated with aging accelerate. Research has demonstrated that cold exposure stimulates autophagy. The thermodynamic stress signals the cell that resources may be scarce and that internal recycling is necessary. The cell responds by activating the autophagic machinery. Damaged components are tagged enclosed in autophagosomes and delivered to lysosomes for breakdown. The recycled materials are then available for building new functional components. Cold effectively triggers a cellular house-cleaning event. The weakest internal components are eliminated and repurposed. What remains is a more functional, more efficient cellular interior. Combined with the apoptosis of the weakest whole cells, the autophagy of damaged components within surviving cells creates a two-level purification. At the cellular population level, the least functional cells are removed. At the intracellular level, the damaged components within surviving cells are recycled. The result is a biological system operating with higher average quality at every scale. This is precisely what thermodynamic optimization looks like in living systems. Energy is directed toward the most efficient structures. Inefficiencies are eliminated. I want to address something specific now. In 2014, researchers at the University of Amsterdam published a study examining the ability of trained individuals to voluntarily influence their immune response through specific breathing and cold exposure techniques. The subjects in that study, trained by Wim Hof, a Dutch athlete known for extreme cold tolerance, showed the ability to suppress inflammatory cytokine responses following injection of bacterial endotoxin. Control subjects who had not undergone the training showed standard inflammatory responses. The trained group showed significantly reduced symptoms. This study was published in PLAS, Proceedings of the National Academy of Sciences, and was considered remarkable because it demonstrated a voluntary human influence over what had long been considered an involuntary immune system function. The mechanism involves the elevated norepinephrine levels triggered by cold exposure and specific breathing patterns. Norepinephrine is known to suppress certain inflammatory pathways. When the cold exposure training increases baseline norepinephrine sensitivity and response magnitude, the individual gains a degree of influence over their inflammatory state. This is not mysticism. This is documented neurobiology intersecting with immunology. The cold trained the nervous system. The nervous system regulated the immune system. The result was measurable and reproducible under controlled conditions. This study does not prove that cold exposure cures any disease, but it proves that cold exposure produces documented, measurable changes in immune function. It proves that the nervous system, properly trained through thermodynamic stress, can modulate inflammation in ways that were previously believed to be outside voluntary control. That is significant. That is the science. Anyone who dismisses cold exposure as a wellness fad has not read this literature carefully. Now I want to address another documented effect. Cold exposure has been studied in the context of inflammation and chronic pain. The elevated norepinephrine that cold produces is not only a vasoconstrictor and metabolic stimulant, it is also an anti-inflammatory agent. Norepinephrine suppresses the production of tumor necrosis factor alpha, or TNF-alpha, which is a key pro-inflammatory cytokine. Reduced TNF-alpha means reduced systemic inflammation. Athletes have used cold immersion for decades to reduce post-exercise inflammation. Sports medicine research has documented the benefits for recovery and reduction of delayed onset muscle soreness. But the implications extend beyond athletic recovery. Chronic low-grade inflammation is implicated in cardiovascular disease, neurodegenerative conditions, metabolic syndrome, and accelerated aging. A tool that reliably reduces norepinephrine, that reduces inflammatory cytokine activity, is a tool with broad biological relevance. The focus and mood effects of cold are also worth understanding mechanistically. Norepinephrine is a key neurotransmitter for prefrontal cortex function, the brain region responsible for focused attention, executive function, and emotional regulation. Low norepinephrine is associated with difficulty concentrating, low motivation, and depression. Several antidepressant medications work by increasing norepinephrine availability. Cold exposure achieves a similar, though temporary, elevation through natural mechanisms. Research has documented that the post-cold elevation in mood and mental clarity, often described anecdotally, correlates directly with the norepinephrine spike. This is not placebo. This is a documented neurochemical event. Dopamine also plays a role. Cold exposure has been shown in research from the Huberman Lab at Stanford University to produce dopamine elevations that are more sustained than those triggered by most other activities. The dopamine response to cold is slow-building and long-lasting compared to the sharp, brief peaks produced by food or social media. This matters because the quality of the dopamine signal affects motivation and well-being differently depending on its duration. A slow, sustained dopamine elevation produces calm, sustained motivation. A sharp peak followed by a crash produces craving and dependency. Cold exposure appears to produce the former. Let me now discuss practical application, because a principle without a protocol is incomplete. How does one actually apply this science? The first approach is the cold shower progression. Begin with your normal shower temperature. In the final 30 to 60 seconds, switch to the coldest water your tap produces. This is sufficient to trigger the cold shock response. The norepinephrine spike begins within seconds of cold water contact with the skin. Practice this daily for 2 weeks, then extend the cold portion to 2 minutes, then 3 minutes. The body adapts, and the adaptation itself is the benefit. As your cold tolerance improves, your thermogenic capacity improves, your norepinephrine response becomes more calibrated, and your BT activity increases. The second approach is contrast therapy, alternating between hot and cold, common in Scandinavian sauna culture and now studied in sports physiology, produces vascular cycling. Hot expands vessels, cold contracts them. The repeated expansion and contraction acts as a pump for the circulatory system. It drives blood and lymphatic fluid through the peripheral tissues and back to the core. Research has documented improved recovery markers following contrast therapy compared to passive rest or heat alone. The lymphatic system, which has no pump of its own, benefits significantly from this mechanical stimulation. The third approach is cold water immersion. ice baths, cold plunge pools, or natural cold water bodies. This produces the most powerful cold shock response of the three approaches. A temperature of 10 to 15 degrees Celsius for 2 to 4 minutes is sufficient for significant physiological response. Research protocols typically use this range. Going colder is not necessarily better. It increases risk without proportional additional benefit for most individuals. The goal is to stay within the hormetic range. Enough stress to trigger adaptation, not enough to cause harm. Timing matters for cold immersion and exercise. Research from the Huberman lab suggests that cold immersion immediately following strength training may blunt some of the hypertrophy adaptations by reducing the inflammatory signals that drive muscle repair. For pure strength and muscle building, a gap of several hours between cold immersion and training is preferable. For general recovery, mood, and metabolic benefits, the timing matters less. The context of your goals should inform your protocol. There is a broader point I want to make before we close. Everything I have described, apoptosis, autophagy, hormesis, BAT activation, norepinephrine release, immune modulation, follows from a single thermodynamic principle. Systems that face controlled, repeated stress develop greater efficiency. This is true of metal alloys under stress testing. It is true of economies under competitive pressure. And it is true of biological systems under hormetic stress. The physics of adaptation is universal. I find it gratifying that the same framework I used to describe the behavior of light and energy in my youth applies with equal precision to the behavior of living cells under thermal stress. The universe does not reward comfort. It rewards adaptation. Every system that survives does so because it adapted to a challenge. Your cells are no different. The weak ones, the ones that cannot adapt, are eliminated. The strong ones remain. The biology rebuilds around the survivors. This is not cruelty. This is optimization. And cold, applied correctly, is one of the most efficient tools for triggering this optimization process that the natural world has produced. If you have found this explanation useful, if you want to understand your body through the lens of physics and documented biology, rather than through speculation and trend, subscribe to this channel. Every video starts with the same commitment: real mechanisms, documented research, no shortcuts, no mythology. The science of cold is not finished. Researchers continue to document new mechanisms. The gut microbiome appears to respond to cold exposure. Mitochondrial biogenesis, the production of new mitochondria, is stimulated by cold. Sleep quality and circadian rhythm regulation show connections to cold exposure timing. This field is young and growing, but what is already established is sufficient to act on. And action, not merely understanding, is what produces results. The cold is not your enemy. It never was. It is a signal, a calibrated ancient signal that tells your biology to sort itself, to remove the weak and reinforce the strong. You have the ability to send that signal deliberately. The protocols exist. The mechanisms are documented. The question is whether you will use this knowledge or continue to avoid the discomfort that every adaptation requires. I spent my life pursuing understanding. The greatest discoveries I made came not from comfort, but from sustained engagement with problems that refuse to yield easily. The discomfort of the cold shower is brief. The biological adaptation it triggers lasts far longer. That is a favorable thermodynamic exchange. Even I can recommend it